Okay, we'll use the notation J for the Jacobian. Okay, so what is the Jacobian? Let's think of, let's see a function, say f, and this function is a function of, function f itself is a vector, so it has multiple functions in it, all one dimension. So f1, q, f2, f3, q, so on till f, m, q. Okay, so m cross 1. So this is like, let's say, sine q, and then cosine q, or sine times cosine q, or q plus 3q squared, so on. So those things which I mentioned are f1, f2, f3, so on, but there are m of them. So it's a vector of functions. Now, q here is the variable on which they depend. Q is itself a vector. So x1, x2, x3. So this is in context of our pendulum, they would be the degrees of freedom, as you see. Okay, so the Jacobian is defined as df dq. So you're taking a derivative of a vector with respect to another vector. Okay, and the size of this is going to be m cross n. It'll have m rows correspond to the functions, n for the f is the dependent, well, q are the independent variables, and f is the dependent variables because it depends on q's. So it's going to be m cross n. So what it will look like is something like this: df1, dq1, dx1, df2, dx2. I'm doing something wrong. So remember, it's m cross n. So m rows. So m rows will appear. So it'll be df2 dx1, df3. Wait, let me just write it a bit neater. So df1, dx1, df2, dx1, df3, dx1, and so on till df m dx1. Then we have df1 dx2, df2 dx2, df3 dx2, so on till dfm dx2. So you get the idea. It's just the same pattern goes on till we end up with df1 dxn, df2 dxn, and so on till dfm dxn. Okay, so now when you think of it, it's not that hard, right? F1 is a scalar function of x1, x2, x3, so on. X1 is, you just take the derivative with respect to x1, keep x2, x3, so on constant. That will give you the first term. And then you just do it for each one. Okay, so I think some people, it's best for them to see an example. So here's an example of how to do this. So example, let's say that f is x squared plus y squared and 2x plus 3y plus 5. And clearly q here is x comma y. Okay. Okay, let's compute the Jacobian. df dq, df1 dx1, df2 dx1, sorry, dx dx, and then df1 dy, df2 dy. Okay, so let's just take the derivative where f1 is clearly, this is f1, this is f2. Okay, so df1 with respect to dx is going to be 2x. So that's the derivative of this term with respect to x. You keep y constant. And then df2 with respect to x, that's going to just give me 2. And then df1 with respect to y. So I take this term, take the derivative with respect to y, that's 2y. And then take this term and derivative with respect to y, that will be 3. So that's my Jacobian. Okay, so this can, in Python, sympy, you can use command called Jacobian to get this. So you don't have to do this by hand, or you don't have to individually code it as df1 dx. You give Python f and q, it'll compute the Jacobian. Okay, so the same example, I just did it in Python, so you know how to do this. Let me just do that to you. Okay, so that's pretty much the code. So again, I'm using sympy, and I need to define x, y as my variables, which means that the final answer will be in terms of x, y, and any numeric values, right? F equals fun x comma y. This is just defining the function f, which is the same one, x squared plus y squared, 2x plus 3y plus 5. I'm using sy.matrix, which is basically defined as a matrix. Then I define z. In this case, this is my q actually, so which is again defined as a matrix. So here I wrote the matrix with still a vector and a vector. So then I need to compute the Jacobians. I do f dot Jacobian of z, where z here is q, and I get the value of the Jacobian in J. So I can make it print this. And then this is just going a step further and saying, what is the value of the Jacobian at a particular point, 1, 2. I just substitute the value of x with z0, 0, which is 1, and then 2. So run this, Control Shift B. This is what exactly I got when I did it by hand. And then if you put the value of x equals 1, y equals 2, you get this answer. Okay, so this is one way of doing it. The other way of doing this is through numerics. That is, you don't really use a sympy toolbox, you just use numpy. Here I define the function f, same thing, but then I use finite difference. So I have a perturbation. I define j to be 0, 0. So 0 having all zeros, then I compute the first column. So this is done by, as I said, finite difference. Okay, so perturb the value of first variable, find the function value, subtract it from what you get when you don't put any perturbation. That gives the first column, and then you do it for the second column. And then to populate the whole thing, you have, this is the first column, this is the second column, and then you can just print it. So this should give the same answer as this 2, 4, 2, 3. So run this. You get 2, 4, 2, 3. Now this is less accurate, right? It's not 2.00, it should be 2, 4. So you see that finite difference gives numeric error. There's a 1e negative 3 error in the solution. The reason why you might be interested in this is that you'll see later on that when you have a code which is not available in symbolic form, like equations 2x, x squared plus y squared, and you cannot use the symbolic package, you need to do it with finite difference. And we'll see instances where we'll be using that. That's why I showed you both methods of how to do this. So this finite difference we've seen before for numerical differentiation, right? Same thing over here, just that it's used for Jacobian.